So we're going to look at 12.1, number 8. I shall share the screen. Again, mine might look a tiny bit different than yours. Let's see. You just copy it down.
It looks like the only difference is 100.
Yeah, I think
Minus. That'll be fine.
well, the bounds, they're written in a funny way, but it just means that x is between 0 and 2, y is between 0 and 2.
Correct. Yeah. So I started off by setting up right the double integral, integral from 0 to 2, integral from 0 to 2 of, in this case it would be 100 minus x squared minus y squared, dx dy. And I wound up getting two 256 over 3 for the exact volume, but that turned out to not be correct. So there we are.
All right. So the only difference yours, what was your number here?
25. So but I mean, if we go through it with 100, it'll be the same thing. It's going to be a nice easy square.
Yeah, it'll just be, it'll be that 100 minus x squared minus y squared dy dx 0 to 2, 0 to 2. Let's work out the inner integral with respect to y. So we just integrate with respect to y and plug in the 2. We get 200 minus 2x squared minus 8 thirds. When you plug in 0, it just drops the whole thing out. Um, and then when I plug, now I'm going to integrate that with respect to x. Now I could combine the constants, but frankly, I'm too lazy. So I get 200x minus 2 thirds x cubed minus 8 thirds x from 2 to 0. I get 400 minus, that's going to be a, so 16 thirds minus another 16 thirds. So that's 400 minus 32 thirds. That would be 1200 thirds. So that would be 1168 thirds. And you swear you did all the steps right and you got the wrong answer?
I I thought I did here. May I share my screen?
Yeah, give me a second here. All right, you should be ready.
Okay. Okay. So it says, oh, which one do you see?
Let's see here, 25 minus x squared minus y squared.
Yeah. Okay. Um, so yeah, it looks. Oh,
Well, I mean, we could, the only changes here, that'd be a 25, that'd be a 25, that'd be a 50 now. So 50, 50x, 100,
yeah. So
uh,
300 minus. Well, hang on. I swear to God, it's something stupid. Let me try this again real quick.
I get a slightly different number than you, but then again, I'm doing it pretty quick. It might just be an arithmetic mistake
Yeah, that's what I'm thinking now. Okay.
because I got the same, I got 268 thirds.
Yeah, that. Okay, thank you. I'll figure that out on my own.
Yeah, I bet you that's all it is. Probably just you made a simple arithmetic error.
Won't be the first time, won't be the last.
Yeah, well, you know what? It never ends. There we go. Um, all right. Since I got this one on the screen here, does anybody have any questions on any of the steps? Okay. So I'm going to share my screen. All righty, let's take a look at this guy. So 12-2, number 14. Suppose R is the shaded region in the figure and f of xy is a continuous function over R. Find the limits of integration for the following iterated integrals. Um, Interesting. It's a circle, obviously. Let me just draw it. And mine's a circle of radius 4. We're setting these up as first dy dx and then dx dy. Okay. So the equation of a circle of radius 4 is centered at the origin is x squared plus y squared is 16, where 16 is 4 squared. If we want to do a dy dx integral, then what you do is you kind of envision like you're gonna, since we're working out dy first, just kind of envision like an arrow going in the positive y direction. And where does it enter and where does it exit? And those will be your bounds. So what you need to do is you need to solve for y. And when you do that, you get plus and minus radical 16 minus x squared. The minus radical is the lower bound. The positive radical is the upper bound. Then the x bound, since it's the outermost integral, will always be constant, so negative 4 to 4. Okay. If you do dx dy, same thing, just make some cosmetic differences. You're going left to right, you would actually solve for x, and you're going to get negative 16 minus y squared as your lower bound. I'm sorry, negative radical 16 minus y squared. Then the upper bound will be radical 16 minus y squared, and then negative 4 and 4 for the y bounds. Is that what you were wondering about?
Yeah, well, watching you do problems on Zoom is so much easier than trying to sometimes decipher the get help by myself. So I
Okay,
that's why I asked that one, just because sometimes the bounds get a little shady. So I appreciate it.
sure. And by the way, when you're dealing with circular regions, have you gotten to the polar stuff yet?
I have not.
Okay. Polar is great because polar handles these circular regions really well. And since I have it up here, might as well do it. Why not, right? Um, so some of you may have already gotten to the polar stuff. I'm going to go ahead and just jump the gun if you haven't. What you do is x is r cos theta, y is r sine theta. You get an extra r from the what's called the Jacobian, and then you do dr d theta. And what you do is you just look at the circle and you draw an arrow from the center outwards, and basically ask yourself where does it start in the circle and where does it end? Actually, it starts when you start drawing it, so it's 0, and then at 4. So these are your radii. And then the theta just tells you to go all the way around the circle, so 0 to 2 pi. So when you do polar, you get much friendlier integrals. For example, you can see that here you just have constant bounds, whereas here you've got these radical bounds. So you'll be getting to polar. If you haven't already got there, you'll be getting there pretty soon. And you'll find that these make these type of integrals a lot simpler.
Yeah, that looks much nicer.
Yeah, when you get there, it'll make sense. There's a bit of geometry that has to be developed, but it does help with these regions a lot because this any circular region in XY coordinates is tough because you're dealing with radicals. All right. Any other questions on this one? Here's some 12-2 questions. And they're all pretty much just double integrals over XY. Stop me if you have a question on any of these. This one's a fun one right here, number 4. Let's take a look at this one because there's a reason I want to do this one. Um, this type of region is often used in later material. Um, it's a tetrahedron. It's basically the YZ plane, the XY plane, and the XZ plane, and then you got a slanting plane kind of cutting through it in the first octant. And so I'm gonna do that one. This is 12-2, number 4. So we got the planes x equals 0, y equals 0, z equals 0. And then we've got the slanting plane x plus y plus z, and I can even draw that, kinda. The intercepts are 9, 9, and 9. So when you have this face that looks right at you, and then you have the 3, 2 in back and 1 on the bottom. Those are the 4 faces of the solid. And so I just want to show you how you can set it up. So this is the surface that you see right here. But what we want to do is solve for z. The bottom plane is z equals 0 because that's the xy plane. So the volume integral the integrand will just be a 1. And we'll have, well, actually, you know what? I'm thinking as I do this, um, I'm just give me a second here. I'm having like a momentary realization here. There's a couple ways to do this question. If I wanted to do it as simply as a d, okay, my bad. I'm going to skip that. This becomes your integrand. I'll explain what I'm doing here. The region of integration is what you see on the base here. And this is something I always try to emphasize with my class you have to see the 3D and the 2D. And this would just be y equals 9 minus x because we're just looking at the xy part. So this is y equals 0 here. So you're just going from 0 to 9 minus x, and then 0 to 9 on the x-axis. That would be the setup. And that will find you the volume. I'm not going to work it out because I just wanted to show you the setup. What I was kind of spacing on is, well, and again, I'm going to ask you, have you gotten to the triple integrals yet?
No, sir, that's 12.5.
Okay. Well, I'm going to go ahead and show this a neat little trick to you guys. You can take any subtraction, a minus b, you can take any subtraction statement and rewrite it as an integral where a and b are the bounds, and you just have a generic du or dt. And stop and think for a moment. Have you ever thought about subtraction in that manner?
No, sir.
Um, Probably not, right? But you certainly can do it that way. One of the tricks in calculus is to take an expression and turn it into an integral. And what I'm going to do here is I'm going to take the two outer integrals, which are good to go, and I'm going to create a third integral. I'm going to call it the dz integral. And what I'm going to do is I'm going to put the 9 minus x minus y in the upper bound and a 0 in the lower bound. And I want you to kind of ruminate on that, mull on it. Would you agree that this integral that I have here is this right here, the 9 minus x minus y?
Yes.
You can see how I turned this expression into an integral. This is a common trick in calculus to go, like to go between the like R2 and R3. And when I did that, I created a dz uh, differential, and then my integrand is actually just a 1. And you can do this. You can, like a regular integral from Calc 1, if I had like 0 to 2 of x squared dx, well, that's the same thing as 0 to 2 integral and then 0 to x squared dy dx. That's a double integral right there. So it's a neat little trick that actually is quite useful. So that's something to keep in mind. The reason I was kind of stalling is because I was going to set it up as a triple integral when I realized, wait a minute, you guys haven't got there yet. So I went ahead and kind of shifted gears and gave you the double integral. But then I wanted to show you how you can turn it into a triple integral. You'll be doing this soon, trust me.
Well, I have a question about one of those.
Yeah.
I don't mind going last though.
No, go ahead.
All right, I'm working on 12.5, number 8.
Okay, give me a second here.
It's one of the ones where it tells you to set it up 6 different ways.
Okay. Yeah. All right. Well, we'll take a look at that.
And I've got a graph so I can share.
Yeah, I've got it. Let me share here. Um, let's take a whack at this one. Does mine look like yours?
Yeah, the only ones I'm stuck on are the bottom 2.
Okay.
I got most of them filled out.
So I'll tell you what. Let me copy the main information here. We're setting up a triple integral, and the bounds are z equals 0, x equals 0, y equals 0. So we're in the first octant. No, my bad, not y equals 0. Z equals y minus 8x, and y equals 16. Okay. To really understand what you're doing here, you got to see what this region looks like. So I'm going to stop the share and I'm going to do my best to draw it. And if I can't draw it satisfactorily, maybe I'll try Desmos. But z equals 0 is the xy plane. X equals 0 is the yz plane. Y equals 16 is a plane out here that's actually parallel to the xz plane. So it's like a wall. Okay, so I've got the xy plane is one bound. I've got the YZ plane as a bound. Okay, then I've got this guy here. Let's try let's try some intercepts. When Y is 0, X is going to be wait, they'll all be zero. Let me try to get a couple points here. So, um, see how best I want to do this here. That looks a little weird. You know what? Let me try this. I'm not seeing this. If I write it like this, uh, 8x minus y minus plus z equals 0. I wonder if that helps me.
Does it make sense to sub in y equals 16?
Well, I'm trying to get the full plane. I'm trying to get this drawn. And eventually, yes, we will have to sub them. But I need to see the y equals 16 actually forms a wall. And so I'm just trying to get a sense of what this thing looks like. And
But what I would do is I would zero out x and draw a line at z equals y, and then
yeah,
and draw a
yeah,
line
that
at
would
z
be
minus 8x.
okay. And then we zero out y, we get z equals negative 8x. Yeah, that's going to give us kind of looks like this. And then it's going to come up. This is a bizarre. You know what? I'm going to go to Desmos. I'm not seeing it. Give me a second here. I'm going to go to the Desmos 3D. Give me a second here. I'm going to share the screen. Okay, I'm getting there. I'm going to have z equals. Oh my God. All right. Yeah. Let me share my screen. So let me try to orient what I've got here. Yes, you can kind of see it. Um, the red is the z equals 0. I'm sorry, my bad. Z equals 0 is the floor, blue. The red is x equals 0. That's the YZ plane. The green is the wall, which is y equals 16. And then this purple is this plane that's kind of just barely, oh my Lord. You almost need to ignore everything except for just this. Let's see if I can get it to orient. Come on. It's a very narrow. Can you guys see that okay? It's the can you see my arrow on my cursor?
Yeah, you've got a wedge that's
Yeah, it's like a very
behind
narrow
the
wedge.
behind the purple shape.
Yeah, so the purple is in front, the red is in back, the green is kind of hidden, but it's back here in this little tiny narrow space, and then the blue, of course, is the floor. All right, well that gives me something to work with. So I'm going to try to draw it again. That gives me something to work with. That's not the easiest thing to see. So we have y equals 16. We have the floor, which is uh, z equals 0. We have the back wall, which is x equals 0. And then we have kind of this front slanting plane, which is this guy right here, z equals y minus 8x. All right. Um, Boy, I don't know. That was tough to see, but now that I see it, okay. So the good news is that when you're setting up your integrals, this is a completely uh, convex shape. In other words, it has no indentations, and there's not going to be any need for setting up more than one triple integral. Um, if I do, I'll do one of them with you. If I do the
Except the
tradition,
problem asks you to set it up all 6 ways.
right? So I'll do one of them, and then we'll jump around. If I do dz dy dx, I'm just kind of looking at this thing and I'm picturing like an imaginary line just kind of running up in the positive z direction. It's going to enter this object at the base at 0. I'll just use generic f for there. And it's going to exit out this slanting plane, which is the y minus 8x. And then I'm done with that. So then what I do is I look at just the part on the xy plane. That's going to be the 16, and that'll be this guy right here. And since z equals 0, I have 0 equals y minus 8x, or in other words, y equals 8x. So now if I do dy, I draw an arrow in the y direction. It's going to enter at 8x and leave at 16. And then my x bounds will be from 0 to 2 because 8 times 2 makes 16. Okay, that's the traditional one. Why don't we jump around? So Dan, let's see. You were struggling with some of the later ones. Is that true? Like number 5, number 6?
The one, yeah, if we jump down to, in my problem, it's the last one. It's dy, dx, dz.
Yeah, let's take a look at that one. So let's dy, dx, dz. All right. Um, so I'm gonna picture an arrow coming in the positive y direction. It's coming this way. What I need to do, if it's coming this way, it's going to hit this slanting plane first. That's going to be my entry bound, and it's going to leave at 16. Well, that's easy. But where does it enter? What I need to do is I need to take this expression and solve for y. So I would get y equals z plus 8x. That would be my entry bound. And now that I'm done with y, so what I need to do is essentially ignore the y dimension. Now, what happens is that this region back here is still in play, and I'm going to basically draw it on the xz plane. I got to be careful here. It's a triangle. Let's see. We know that this is the line z equals y, so that'll also be a 16. It's going to be a triangle like this. And we already established this will be a 2. Okay. All right, so now I'm going to do a dx integral. I'm going to draw my arrow this way. It enters here as x equals 0. Now it exits here. We got to come up with an equation. If I do the traditional z, the slope is -8 and the plus 16. I can just kind of move some things around. If I solve for x, I get z, take away 16 divided by -8 equals x. And that becomes my exit bound. That'll be -1/8 z, and then -16 over -8 is 2. And then your x bounds, well, that's the easy one, 0 to 2. I kind of ran through that quickly. Does that help?
Uh, yeah, I mean, like it's easy to do algebraically. I feel like I've I've sat here and I've gotten 4 out of 6 of them correct, and I've done it algebraically. I've come back the next day, and the answer that I think should be right is still wrong.
Huh. You know, if you're still getting wrong, put it on ed discussion and show what you got. And maybe we can, reverse engineer it and figure out. But so this is how I would have worked it out. So really, you got to see the region, um, and I'll admit this guy was tricky, but we got it. All right. Does anybody want to see another one on this one, or are you good to go?
Yeah, I'll chew on it some more, and then if I can't get it, I'll post it to Ed.
Yeah, that would be good because really, I can only guess why you're getting them wrong. But if you show your steps, it'll help a lot. We can probably figure it out pretty quick. All right. Woo.
Is on exam 2, correct? Because in modules, it's in module 5, and I just wanted to be sure that it was on exam 2.
You know what? Let me double check that. I always forget because we have kind of a funny break. Um,
Yeah, because on our screen for modules 3 and 4,
no,
which
it actually only goes up through 12.3.
okay, so 12.5 is saved for exam 3, the final.
Yeah,
Okay,
which is basically exam 3.
got it.
So yeah, because it's yeah, okay, I see what's going on here. We actually have 12.5 kind of grouped in with the earlier stuff, but the exam only covers through 12.3. Let me check something on the due dates. I did a little tweaking of the due dates recently. I've got 12.5 set for Feb 20. I might actually, you know what? I'm going to bump that back. I'll do it right now. I'll make it to the 23rd. And that way, yeah, there we go. So I've grouped it in with the stuff that will be on exam 3.
Cool, thank you. I do
Good.
appreciate you also moving the due dates for the homework around. I did notice.
Yeah, no problem. I went through and now that we're about 5 weeks into the term, um, and I can see where you guys are at, it made a little more sense to kind of do a little moving around. And I'm also doing it for myself so that I can be available to help you. Otherwise, because there's those down days and I'm just simply not available.
So would it be correct to say then that exam 2 is going to be 11.1, 11.3, 11.4, 11.5, 11.6, 11.7,
Correct.
12.1, 12.2,
And 12.3.
and 12.3. Okay.
Yep. That will be that. Yeah. And by the way, make sure you guys are doing the practice test. Have you been working on that?
Planning to start it this week.
Yeah. Just like last time, you get multiple attempts. It's an excellent guide for what to expect on exam 2. And I also will include it in your grade. What I did is I just rolled it in as 2 extra credit points out of 2. So if you did like half, you got 1, for example. But more importantly, I think it actually played a role because exam 1 grades were pretty good. I was very pleased. So I want you guys to do the practice for exam 2.
Yeah, the practice exam helped out a lot. I really appreciate it.
Yeah,
Some classes that doesn't work the same. They give exam reviews and then they don't help out on the test.
yeah, the courses are constantly being added to and tweaked. So I'll be honest, the practice exams look new to me. I didn't create them. Um, I think they're brand new for this semester, so you guys got lucky. How are you guys doing with polar? I barely touched on it, but do you have any questions on polar on 12.3? You know what? I'm gonna bring up one that actually came up in ed discussion. It's number 8. It's kind of a famous one. You've got this region that looks like a half, whatever you want to call that, um, half a frisbee. I'll draw it. It's 2 circles, one of radius 3, one of radius 4, and it forms a half a ring. And you need to set up an integral in polar. Okay. Um, my picture's not as pretty as theirs. So any circular type region should be rendered in polar because it just makes the calculations easier. And I'll show you that trick where you just draw an arrow from the origin outward. Where does it enter and where does it exit? It enters at 3 and it exits at 4. So that tells you your radii, your R values will be between 3 and 4. Now that's the easy one. The tricky one is the angle that sweeps this out. And the angle always needs to be swept counterclockwise. You always want to go from a lower value to a higher value. Now, some people will look at this and say, well, that's 270 degrees or 3 pi over 2 radians. Well, not here. Actually, what you want to do is you want to go backwards and then start your sweep. So if you go backwards, you'll actually start at negative pi halves and you'll sweep up here to positive pi halves. And that would be your bounds for this case right here. Now, when you set up your double integral, you're going to turn whatever your integrand is into r's and thetas. You're going to have an extra r from the Jacobian. And if I do dr d theta, and I think you have to type it in as dtheta in the homework, well, then you just pop on the bounds. The bounds are 3 to 4, and the thetas is negative pi halves to pi halves. And it makes a lot of these calculations a lot easier. A question I'm going to give you guys one that looks like a nightmare. It's a double integral in xy coordinates. Give me a second here. Let's see, I'll just make one up. So let's see from doing this from my memory, so hopefully I'll get it right. Oops. Nope, I want that to be a 0. All right, this should work. It looks like a nightmare. Let's be honest. It looks like a nightmare. Certainly if you tried to integrate, I mean, you can work it out. It's going to be x squared y plus 1/3 y cubed. But then you got to plug these guys in. And now you've got radicals inside cubes and stuff like that. That's just going to be ugly. So the beauty of this is that if you recognize what you have here, um, especially from the bounds, you actually have a pretty easy shape. These are partial circles, one of radius 2, one of radius 3. And what I've done is I've set up the first double integral to be this part right here from 0 to 2. So it's basically capturing this bit right there. you'll notice my y value, I would be entering through the radical 4 minus x squared and exiting radical 9 minus x squared. And then this double integral takes care of the part from 2 to 3. Okay. But man, I don't want to screw around with radicals. So what I do is I turn everything into polar. The x squared plus y squared becomes r squared because that's the relationship. Remember, you just use that relationship. I'll put it over here. You have x, y, and r, so that's just the Pythagorean relationship. You're going to get an extra r from the Jacobian. And we're going to have dr d theta. And then you just look at the picture here. Your radii values, if I draw an arrow just outward, range between 2 and 3. And your theta values are between 0 and pi halves. And so I can clean that up a little bit. Now I have r cubed. And then the other bounds stay the same. And so I ask you, given a choice of working out a double integral, which one would you like to do? You see what the advantage of polar is? When you get something nasty like that. This thing, I mean, I'll in my in-person classes, I usually give a question like this on an exam, and I tell the students, don't be intimidated by it. You know, it's just a nice, easy shape, but the trick is you've got to see the shape. If you can see what it is, and then just infer the bounds off of that, it suddenly becomes a real easy problem. If you can't see it, then you're stuck. But you know, we really try to emphasize that. Any questions? Let's see. Um, well, you know, as usual, just you know what? Well, we got a few minutes. Let me just bring up one more on the. I'm just scrolling through. This is number 13 in section 12.3. You got all these crazy looking regions here. These are kind of fun, actually. The easy one is F. It's just a full circle of radius 4. So your radius bounds would be 0 to 4. By the way, in polar, you never ever need negative radii. So you picture an arrow being drawn from the origin outward. Now, outward can be any direction. Okay. So this one's going to have r bounds from 0 to 4, and your theta bounds will be 0 to 2 pi, and that will be this guy, number 7. And then E is a partial circle, looks like radius 5, so 0 to 5. And this one's being swept from negative pi halves to 0, which is, where are you? Well, actually, my negative pi halves to, well, I see what they did. All right, it's this one right here. It's number 1. They just, okay, they took the equivalence, 3 pi halves to 2 pi, as long as it increases in value. Okay. Negative pi halves to 0 would probably be a little easier, to be honest. For something weird like D, let's see if we can figure this one out. The bounds, the region begins at radius 4 and exits at radius 5. And we're starting back here at negative 45 degrees and sweeping up to, would that be 135? So that would be negative pi fourths to 3 pi fourths. It's this guy right here, number 6. So anyway, it's just kind of a challenge to try to infer the bounds off the thing. And I've noticed that they scramble a little bit. Some of them have d theta dr, some of them have dr d theta. Generally, it doesn't matter. As long as your bounds are constant, the order of integration doesn't matter. But I think you'll find it easier usually to do dr d theta because you can take care of that r immediately. That's generally why we do dr d theta in that order. Number 14 would be kind of like I just got done talking about. If you can see what this region is, it's actually a pretty gentle looking region. I can tell you right now, it's basically a wedge of a circle. Now you might look at the bounds and you might think, oh man, yuck. But this is just the 45-degree line, x equals y. This is a circle of radius 5, so just draw them and then just kind of figure out in your y direction, this would be the x-axis. This would be a point on the circle. And it would have to agree with the 45-degree line. So I think we can already figure out that the bounds would be like 0 to 4, no, 0 to 5 for r. And looks like it's going to be 0 to pi over 4 for the, actually, it looks like it'll be pi 4 to the pi halves. Anyway, draw the region. I'm trying to do this in my head. Anyway, yeah, and then this guy looks like a lot of fun too. Oh my God, you guys are so lucky to be doing this. All right. Do we have any last questions? Well, in that case, I'm gonna, well, bring it back to me. Thank you all for joining. I'll get this thing recorded and post it onto the website probably in about a half hour. And in between now and next weekend, just keep on posting questions to Ed Discussions. So I appreciate you guys joining me again, and have a safe Sunday night and safe week. So I'm going to go ahead and count down. 3, 2, 1, bye.